stream to start and video recording. And yeah, okay, looks like we are all set. So welcome to the second of my 5 lectures during this camp. Yeah, looks like we don't still have everybody, but let's punish them by starting at least a little bit on time. Okay, so today's lecture will be about at least 2 mostly separate topics. I will start by talking about invariance in some specific settings, and then I will continue talking about some uses for randomness, and we'll be solving some problems along the way, and we'll see what happens. So, invariance. Invariant is from Latin, and it means something that doesn't change. And these are usually some mathematical constraints that are necessary but not sufficient conditions for some solution to exist or for some property. And one of the most basic invariants you have definitely seen before is coloring something like a chessboard. If you have a board like this and you want to cover it completely with dominoes that have size 2, is it possible or is it not possible? Well, you can argue with the chessboard coloring that it is not possible because every domino will cover a black one and a white one, and you have 5 black ones and the 4 white ones. And if you are already awake and you started thinking, then you are realizing, okay, why is he using checkerboard coloring at all? Because the area of this is 9, and 9 isn't divisible by 2. So there is an even simpler invariant. Whatever you cover by dominoes will have an even area, and this has an odd area, so it cannot be colored. Yeah, but of course, there are some other shapes, like this one, where the area is 6. So the first invariant doesn't help you, but if you look at the black cells, there is 4 of them. If you look at the white cells, there is just 2. And this is a very simple argument you can make for this not being coverable by dominoes, so you don't have to brute force over possibilities. You can just look at it and say, there, obviously, this invariant doesn't hold. So this is the type of properties you have to look for in problems, and sometimes they're trivial and easy to discover, sometimes they're not. So one of my favorite versions of this, like coloring and checkerboard and similar invariants, is the following one. So suppose you have a rectangular board, R times C, and you want to cover it completely with tiles that are of the shape of a Tetris L. You can rotate it arbitrarily, you can even flip it around, so you can use the L and the J as well. And the question is, for what values of R and C is this possible? And, well, one obvious necessary condition is the area has to be divisible by 4. But is it really sufficient? And there is a neat trick that can be used to show that actually not all of those rectangles are still colorable. And the neat trick is that you are not using checkerboard coloring, because that one doesn't really help you. If you color it like a checkerboard or chessboard, you will get 2 black and 2 white ones on each of them. So it will give you essentially the same constraint that you got already from the area. But one thing you can do is you can color every second column. And what happens now if you place these L's onto the board? If you place it like horizontally, it can look like this, or it can look like that. So in this case, there are 3 black cells and 1 white. In this case, there are 3 white cells and 1 black. And also, if you place it vertically, wherever is the vertical leg will cover 3 cells of the same color, and then you will get 1 cell of the other color. So for this particular type of coloring, you will always cover 3 of one color and 1 of the opposite. So if you choose an even dimension, so if this is even, and you color it according to this even dimension, what you get is exactly the same number of black and white cells. And this means that not just you don't just have to have the exact number of Ls, but you have an extra constraint that the number of Ls that are mostly black has to be equal to the number of Ls that are mostly white. So in addition to covering the entire area, you get new information. So for this particular rectangle, for the tiling to exist, the number of Ls has to be even. So if you have something like, let's say this is 12 and this is 9, then you can compute that 12 times 9 divided by 4 is 27. So just from the area, it would seem like this rectangle has an area divisible by 4, and it should be coverable by the Ls because it's divisible by 4. But you cannot cover this rectangle with 27 Ls because you will have more Ls of one color than of the other. And yeah, so this is an example of a much trickier invariant that can be done in some of the problems. And there are all kinds of techniques how to come up with invariants like this, and you can use like coloring along diagonals, but not just using 2 colors, but maybe 3 and 4 if you are tiling using long straight pieces, and so on. So after this very short warm-up, let's give also everyone here a little bit to think about. And the problem we'll be talking about now is a problem that starts with the same setting that is used in many of like peg jumping solitaire games. So we will have again some kind of a grid. On the grid we will have some tokens, and the tokens can jump each other. If you have a token, another token, and an empty space, you can make a jump, and this token you jumped is then removed from the board. This is a very common setup. Like it was most originally and very commonly it is used in some kinds of like peg solitaires, as I mentioned. So you have some board with some of these tokens already placed, and you have to find a sequence of jumps such that they will eat everything except for one final token that will stay somewhere on the board. So this is a logic puzzle for a single player. We will do something slightly different with these tokens. We will send them to explore enemy terrain. So suppose there is an infinite square grid, and the x-axis of the grid is the boundary between our promised land, which is everything below the line, and enemy territory, which is everything above the line. So I will make this line thick. And now we are planning to go explore the enemy territory. And the exploration will have 2 phases. Well, the first phase will be preparation, when we prepare some explorers on our side, and then there will be the exploration itself happening. So for the preparation, we have to place 1 or more tokens onto the board, but all of them have to be placed in the bottom half. And once we have done so, we can use these jumps to move the tokens, and we want to send the token as far as possible into the enemy territory. So I will start with the very easy examples. If we want to reach line 1 of enemy territory, what is the minimum number of tokens we need? Well, obviously it is 2, because if you place just 1 token anywhere, we cannot make any jumps. If you place 2 tokens like this, then we can do this one single jump, this one gets eliminated, and there will be a token here. So in order to get to line 1 of enemy territory, what we need is exactly 2 tokens. This is the optimal solution. What is the optimal solution for line 2? Again, 4 tokens, and it should be pretty obvious. We can do something like this. So the starting configuration is these 4 tokens, like this. We start with the same jump as before. And now we can take this token, jump over this one. So now we have 1 token here, 1 token there, and jump over that one. So this one is eliminated. We started with 4 tokens, 1, 2, 3, 4. We ended up with 1 token over here. So line 2 requires 4 tokens. Anyone care to guess what the next number here will be? Right? Yeah. Okay. So, show me. Feel free to grab pen and paper and try to come up with a configuration that will get one of the tokens to the third line. Yeah, that works. Okay, I'll give you a bit more time to think. Feel free to wave at me if you think you have it. Okay, looks like we are starting to get a few people. Sorry? Yeah, okay. Thank you. Okay, so one more time, like informal show of hands, wave at me if you think you know how to solve it. Okay, well, so let's show everybody else. You were, I think, the first, so you can tell me your solution, what it was, or you can even come to the show if you want. Yeah.
I just have added these four, and the idea is after this is done and we'll have a stone here, we can move these two over here and then move this one here, and
Yeah.
it's able to do it.
Yeah, that's perfect. This is a configuration that works. It can be shown by exhaustive search that it is actually optimal. There is also a second valid solution where these two are not there, but they are here. But they are doing exactly the same thing. So first you use these 4 tokens to get one of them here, and then these two will get one here, these two will get one here, and those two will be able to do this jump and that jump, and you have a token on line 3. Okay, so now pattern matching exercise. What is the answer here? 16, now 20. Why is the answer 20 and not 16? Well, this is actually a very practical lesson that is hiding behind the answer being 20 and not 16. It would be 16 if you were allowed to have multiple tokens in the same cell and like reuse the same locations and get another token closer quickly. But like the place is already occupied by these ones that you needed to do the earlier steps, and if you need to place the others slightly farther away, then you need more of them to be able to push one of them closer enough. So that's like the general idea what's going on. And this kind of thinking has also implications in the practical execution of like distributed algorithms. The distributed algorithms you may have encountered are algorithms where you are operating with the assumption that you have like an unlimited number of processors, and then they are together trying to solve one large instance of a problem, and each of them is working on some small part, and they need to somehow share information. And this sharing of information is something that you can have in a theoretical model, But as you are scaling things, it is not obvious that you can have it in constant time in the physical realization, because like not all of the actual processors can be close to all of the others, because you are physically limited with three-dimensional space. So if you have one of them and the others will have to be in spheres around it or whatever, it's all packed together, but still some of them are farther from each other than others, and you can only pack a finite number of them into an enclosed area. So as you are trying to scale your distributed system, you can run into issues with like proximity being no longer guaranteed. And this is something we are seeing here. So for line 4, there are, again, several optimal configurations. We have done the brute force search, verified that there is nothing smaller, and the smallest number we can get is 20. Okay, so now that I broke your initial expectations of this being just powers of 2, let's guess the value number 5 in this sequence. Then just shout numbers, whatever you think is the next one after 2, 4, 8, 20. What is the fifth one? 150. Anyone else? Omega. Over small? Yeah? What was that?
Omega, infinite.
Infinite. Any other opinions?
At least 80?
At least 80. Anyone else want to get their guess in before we make the reveal? Okay, so I will not do the reveal yet. I will postpone it until we have something more to work with. And instead I will talk to you about a completely different problem. Afterwards we will get back to this one and we will show what the deal with it is. And the different problem looks like this. There is a castle here on cell number 0. And there are some people trying to reach the castle on all of the other cells. And this is a 2-player game. You are given the initial configuration. Oh, sorry. You don't need a second player. Sorry for the confusion. So there is an initial configuration of the people as they are distributed on the cells, and 2 things are happening alternately. So one of them is that, okay, I should think before I speak. That's a very good lesson for everybody, but especially for me now. So let me start by describing the initial configuration first, and then I will talk to you about what is actually being done with them. So we have, for example, you are given the input as a vector of numbers. So for example, you are given the information that there are 2 people on this cell, there are 3 of them on that one, this one is empty, this one is also empty, this one has 17 people, this one has 3, and this one has 1. And now you do have 2 players. One of them is trying to have somebody reach the castle, and the other is defending the castle. And the game is played as follows. The player that controls everybody that is going towards the castle, in each step of the game, has to divide the people into 2 categories. So everybody will get a blue hat or a red hat. And then the person defending the castle can choose a color and send everybody of that color home. So we can say that, for example, we will divide the people as follows. So there will be 1 blue and 1 red among these. All 3 of these will be red. Out of these, 4 will be red and 13 will be blue. These ones will all get blue hats and this one will be red. So this is one possible division we can have. And now the person defending the castle can say red go home or blue go home. Whatever they choose, we do. The red ones go home. And the ones that remain get to advance 1 step closer to the castle. So now instead of the initial configuration, we will have a 1 here, a 13 here, and a 3 here. And the game starts from the beginning. So again, we discard the original colors, and now again we divide these people into two groups. One of them is sent home, the other gets to advance. And the question for this game is, what is the optimal strategy for one player? What is the optimal strategy for the other player? Given the initial configuration, who wins the game? And there is an example of a game that is very different from the games like NIM or similar stuff that we had yesterday, but at the same time, you can maybe find some similarities if you think hard about it, but we don't really have to, because like intuitively it is pretty easy to see what's going on. And the intuition is as follows. So let's focus just on these two. What can you get if you have just two people here? If you give both of them the same color, both of them will get sent home. If you get one blue and one red hat, then one of them will be sent home, and the other one advances one step closer. What would happen if you had 4 people here? Again, if you had just the 4 people here and nothing else, it is obvious that you want to split them exactly into halves. If you do any kind of a unbalanced split, you will just get less than half of them remaining, and the bigger part will be sent away. So 4 people here can get you 2 people there, 2 people here can get you 1 person here, and that is still not enough, because you will give them a head of 1 color and the defender will send them home. So clearly, if we had to place everybody on the same cell at the beginning, we need 8 people here to have 4 there, to have 2 there, to have 1 here. So a person here is worth like half a person inside the castle. A person here is worth 1/4. And this is the intuition we are getting from observing what is going on in the game. So this brings us to a theory that let's assign some kind of like weights to the cells. So this one will have weight 1. This will be 1/2, 1/4, 1/8, 1/16, 1/32, 1/32, and so on. And now, when we have any initial configuration, we see an invariant. We see that what's going on here is that so suppose that you look at the numbers of people you actually have at the beginning, and for each of them, you count them with a specific weight they have. What happens now if the sum you get is strictly smaller than 1? And it should be reasonably obvious that in this case, you can never win the game if the defender of the castle is playing the game optimally. What will be the defender's strategy? Well, you split the people into 2 groups as arbitrarily as you like, and if the total sum was below 1, then the smaller of those 2 groups, if you again sum their weights, will have a weight of below 1/2. And if the defender of the castle simply again looks at those weights, sends the heavier group home and keeps just the lighter group, then you are left with a group that is worth less than half, and even when they advance 1 step to the castle, so everybody's weight now doubles, the new weight is again below 1. So the defender has a very easy strategy. Look at the total weight of each group, send away the bigger one, keep the smaller one, and if the initial sum of weights is below 1, then after every step it will remain below 1. In fact, it cannot increase. This is the invariant. And by maintaining this invariant, the other player eventually has to run out of people, because they will never be able to reach the castle. They will never have a sum that is 1, so a figure that is actually standing at the castle. So if the total sum of weights is below 1, then we cannot win. What happens in the opposite case? If the sum of weights of all the people is 1 or greater than 1, I claim that we can win. We can always find a strategy to reach the castle. What we need to do should be obvious. Whenever we are splitting the people into 2 groups, we have to do the split in such a way that each of the halves has to have a total weight at least 1/2. This will preserve the invariant. It may not be possible in some cases to split the people equally, like if you have 3 people with 2 of them here and 1 of them here, then there will not be a perfect split, so we cannot hope for a perfect split, but it is sufficient to have a split where like one person will be blue and these ones will be red, because now this person alone has weight 1/2, this group has weight more than 1/2, and regardless of which one of them the opponent sends away, the ones that remain and make one step closer to the goal will now again have weight at least 1. So the last thing we need to show is that such a split always exists, and what you can do is you can just sorry. So the thing I claim now about this is, yeah? Yes, yes. That's exactly the right observation. And this is something you will get not just with these particular weights, but you can get it also with some various coin systems. Like if you are divisors, or if there are divisors of each other, and not necessarily completely, but divisors of whatever you need to achieve, then you should be able always to find exact subset. So the claim here is that regardless of what the actual collection of weights we have, if the sum is greater than 1, you can always find a subset with a sum of exactly 1/2. And you can essentially do the proof greedily. So we will start paying or putting people into the set from the biggest ones, and you greedily move on. And during this process, you will, if you are forced, so you can never be forced to jump over 1/2 and not have anything smaller because of those numbers dividing each other. I can do the proof nicer if you need it, but I think it's instructional to go through the technical details on your own and then try to come up with the details of how to prove it. So the claim is that there will be always a possibility how to give blue hats to people who have sum of weights exactly 1/2. The other group will then have sum of weights 1/2 or more, and regardless of which one of them is chosen, after the step closer to the castle, again you will have sum of weights equal to 1. And in all cases, what's also happening at the same time, so in both cases when we are losing, when I claim we are losing and when I claim we are winning, there is not just the invariant that the sum of weights remains above the boundary or below the boundary, but also you can notice that in each step at least one person always gets sent away. So the game has to be finite, and after finitely many steps the game has to terminate. And if we are guaranteed that the sum of weights will always be 1 or more, then at the moment when the game terminates somebody has to be here. And if we are guaranteed that it is always less than 1, then at the moment when it terminates this has to be empty, and that's it. So armed with this knowledge, armed with this observation, that sometimes it makes sense to think about assigning different weights to different positions depending on how far you are from the goal, we can now go back to this problem. And this is a problem you will find in literature or even on Wikipedia under the name Conway's soldiers, and this is the same John Horton Conway that was doing all kinds of other things in game theory. And so let's start thinking about row 5. And we will try to show how difficult it is to get a token to the 5th row of enemy territory. So in order to start, let's pick a specific cell in row 5, and let's say that this is our intended destination. As this is an infinite plane, this doesn't matter. So we can choose a cell arbitrarily, but we will choose one specific one, and we will say that now we are looking for configurations of the initial tokens such that after a series of jumps, this is exactly the cell where we want the token to finish. And now what do we have here is that these two tokens, this one and this one together, should have the same weight as a single token on the goal. And this token should have the same weight as these two tokens, because these two tokens can produce this one. And so on. So again, as in the example before, as we are going farther and farther away from the goal, the rate of having a token in this particular cell should decrease. And it's pretty obvious that decreasing exponentially is what we will have to do in some sense. So let's try doing that. So let's say that the final cell, as before, will have weight 1. And now one step closer will be some x. We don't know what the constant is yet, but we will determine it very quickly. This will be x squared, this will be x squared, this will be x squared as well. These are x, these are x cubed. This is to the power of 4, power of 5, power of 6, and so on. And now, from any three of these blocks, but it is easiest from this one, we get the equality that will tell us what the x is supposed to be. So 1 is supposed to be equal to x plus x squared plus x minus 1 equals 0. And this has two solutions. So this is minus b plus minus square root of, what is it? Should I derive it on Scratch when I don't remember it? B squared 1 plus 2 minus 2ac plus 4 divided by 2, right? So so we want not the negative one but the positive one. So we want the x is square root of 5 minus 1 divided by 2. This is like I think this is the reciprocal of the golden ratio. This is the 0.608 and something. So this is the specific value of x we are going to use. And with this value of x, if you have two tokens and you make a jump towards the goal, the total value of your tokens will remain exactly the same. If you are making suboptimal moves, let's call them, and make a jump away from the goal, then the value of your collection will actually decrease. But there is no jump that would make the value of your collection of tokens increase. So whatever original configuration you make, the sum of the weights of these tokens has to be at least 1. Because it cannot grow, it can only decrease if you are jumping away from the goal. So now a necessary condition, an invariant that will be preserved during the process, is that we need to start with a configuration of tokens that has the sum of weights at least 1. And now comes the surprise. The claim that the answer here is infinity was actually correct. So there is no finite configuration of tokens with this property. And you can actually do the math yourself. It's not that hard. So what is going on here is, if you look just at this column, what you have here is a geometric series. So this is x to the 5 plus x to the 6 plus x to the 7. You can use the formula. You can get the result for this. You can do the same over here for every column. You are just starting from one higher index. The same here. You get another, I think, a purely geometric series here on the bottom. You sum that up, and you will get that the sum of this entire infinite plane is exactly 1. So it turns out that if you have filled the entire plane with tokens, you would get exactly the total weight 1. So any finite configuration, which is only a proper subset of this, will have a weight that is strictly smaller than 1. So even if you do a billion of tokens and then a billion minus 1 jumps, you will never get to the 5th row because the total weight of tokens at the beginning is less than 1. It will remain less than 1 during the entire process, so none of them can reach the specific final cell. So the problems with the density and packing the tokens as close enough to the start as you need them is actually growing really, really surprisingly quickly. And for the 4, it was only forcing us to use 4 extra tokens, but for the 5, it makes it impossible. Let me give you one last problem from this category. And for this one, you can think about the solution then on your own. And the problem looks as follows. This time we have just the one positive quadrant of the infinite grid. And at the beginning, we have a single token sitting here. And whenever so this is a game again played in turns by a single player, and in each turn we can find any token such that on top of it and also on the right of it is an empty space, and we can click on it and it will disappear and it will be replaced by 2 tokens that are sitting in those cells. So now I can click this one, it will disappear and be replaced by those 2. At this moment I cannot click on the bottom one because it doesn't have anywhere to go on the top. But I can click on this one, it will be replaced by those 2, and then I can click on this one, it will be replaced by those 2. And I can play this game in this way essentially forever. And now you can notice that the original cell is already empty, and also the next diagonal is already empty. This is nice. We would like to have as many empty diagonals as possible. And the question for you to answer on your own, first of all, is it possible to clear arbitrarily many diagonals, or is there some kind of finite limit? And if there is a finite limit, what it is? If it is possible, how to do it? So either try to find a sequence of clicking that will guarantee that eventually you will clear the next diagonal, then the next one, then the next one, or find an argument why this process has to stop and why there is eventually a diagonal that will never be empty. If you really get stuck, talk to me some other day and I will give you some hints how to proceed with this problem, but you should be able at this point to solve it on your own. Okay, let us now do something slightly different. The next thing I'm going to talk to you about is an interesting mathematical result about some kinds of probability. So let's introduce the result with a very simple problem again, because thinking about problems is fun. And the problem is as follows. There is a ship, and the ship just came into harbor. On the ship there are n cabins numbered from 0 to n-1. And in each cabin there is a single sailor that lives there. And all n sailors have now gone ashore to the pub. In the pub, all of them got drunk. And then in early morning hours, all of them staggered onto the ship. And each of them, in their current state, has picked a cabin completely at random, opened the door, fell inside, fell asleep. And now there isn't even a limit on the number of sailors in the same cabin, as you can imagine. So even if there are like already 3 sailors sleeping there, it is perfectly possible that the next one, when they come to the ship, they will open the same cabin and fall on top of the pile. And in the morning, all 4 of them will awake in the same cabin with a headache and no memories of what has happened. So each of them chooses the cabin where they will sleep uniformly at random. All of those choices are mutually independent. The question now is, what is the expected number of sailors who wake up in their own cabin. And now if you are not a big fan of probability yet, if you are more of a fan of combinatories, you can turn this into a counting problem. So what is this expected value? This is an expected value of any discrete variable, simply the weighted sum of results. So if you have if you are rolling a die with values 1, 2, 3, 5, 4, 6, then and all of the faces are exactly the same likelihood to come up, then the expected value of your roll is the weighted average of the values on the faces. So with probability 1 over 6, you will get the value of 1. With probability 1 over 6, you will get the value of 2, and so on. So for a single die roll, the expected value is, with probability 1, 6, you get 1. With probability 1, 6, you get 2, and so on. And this weighted average of possible outcomes is the expected value. So in other words, if you were repeating the experiment many times and summing up the results, the average would converge to this particular value. That's the meaning of the expected value, average over many experiments. So you can now do the counting, that what is the number of configuration of sailors where nobody sleeps in their own cabin. These are the derangements. This is the yes?
You explain it again?
Yeah, the problem is as follows. So you are doing essentially very simplified hashing with the sailors. So at the beginning of the process, there is an empty boat with n empty cabins, and there are n sailors here. The sailors are numbered from 0 to n-1, just as the cabins. Each of the sailors, at some point, comes to the boat, chooses a cabin uniformly at random, and stays there. And in the morning, when all of the sailors are already back on the boat, for each of the sailors, we are looking at whether or not they wake up in their own cabin, and we are asking what is the expected number of sailors. So if you do this once, it's possible that nobody will wake up in their own cabin. If you do it another time, there will be 3 such sailors. If you do it one more time, there will be 1 such sailor, and so on. And the average over many experiments will eventually converge to some number, and we are asking what it is. And as I'm saying, you can turn this into a counting problem, but it would be pretty nice. The math to count all of the sequences in which the sailors, none of the sailors wake up in their own room. I mean, yes, you can do it. It's not as difficult as that it would be impossible. So for each sailor, so if you want to count the configurations where nobody is in their own room, then for each sailor you have n-1 other cabins available. So this is n-1 to the power of n configurations where the answer is 0. The configurations where the answer is 1, you have to choose the sailor who is in their own room, and for each of the other sailors you have to choose the other room they are in. So this is n-1 to the power of n-1, and so on. And you could do the counting. So with this, in these many cases you will get the answer 0, in these many cases you will get the answer 1, and so on. And you sum it up all together, and then you divide the entire sum by n to the n, which is the total number of configurations of sailors, and you will get the average number of sailors in their room. So you could do this math. It will be a little bit painful, half a page, and you will get the result. Or you could look at this problem through a different lens, and the lens is the statement called the linearity of expectation. And this is a very, very useful tool in problems about probability. And to understand what it is and why it works is imagine that we are doing the experiment very many times, and we have created a very large table. So here on the top are the sailor numbers, and here on the left is the ordinal number of the experiment. So the first experiment, second experiment, third one, and so on. So every night the sailors go ashore, they get drunk, they come back at random, and every morning we record the result of the experiment. So we will place zeros for those sailors who woke up in incorrect cabins, and we will place ones for those sailors who woke up in the correct cabin. And as we are recording the many various experiments, you are getting a table with some ones and some zeros. The question about the expected value of this variable, the expected number of sailors who wake up at home, is the question, what is the average number of ones per row in this table? And the whole trick is that you can, after you imagine this whole very large table that can be as long as you want it to be, instead of looking at it one row at a time, we can look at it one column at a time. And what happens in a single column? In a single column, you have a single sailor, and in each of those experiments, the probability that the sailor will end up in their own cabin is simply 1 over n, because they choose one of the n cabins at random, so probability they choose their own one is 1 over n. So on average, every n rows, there will be a single one in this column. So if you have some very large number r of rows, you can expect an average of r over n ones in this particular column. And the same argument can be done about each of the other sailors as well. So each of them, each of the n columns will contribute this many ones on average. So the total number of ones we expect per table is r, and therefore the number of ones expect per row of the table is exactly 1. And the slightly more mathematical version of doing this is simply that the expected value, so what we have here is we can view it as a sum of n random variables. So for each sailor, we will have a random variable, xi, that is either 1 or 0. 1 means that sailor number I chose their own cabin. 0 is that the sailor did choose somebody else's cabin. For each individual I, it is obvious the expected value of xi is 1 over n. We have a single sailor with probability 1 over n. The value of this variable is 1. With the probability n minus 1 over n, the value is 0. So this is the expectation. And the total expected number of sailors at home is simply the expected value of the sum of all of these random variables. And the statement about linearity of expectation is telling you that the expected value of a sum is simply the sum of the individual expected values. And on its own, this is not very surprising, but this is a very powerful statement. And the important thing about it is that it doesn't really care about anything about these random variables. They don't have to be independent. There can be any kinds of dependencies between them, and the statement still holds. And the intuitive argument why it holds is exactly the same I was doing here with this table. So if you are writing down such a table, and for each of the variables you are writing down its exact value in each of those experiments, then for each of the variables separately you can consider its column, and the average of that column will be determined just by this single variable. And the average of the column is what is contributing on average to a single experiment. So if you are doing an average over very many experiments, you have to get the same average if you are averaging it row by row, or if you are averaging it column by column. So whenever we are interested in the outcome of several different things together, you can just consider each of them separately. These individual expected values will be usually much easier to calculate, and you just then sum it up together. So instead of doing all of these combinatorics, if you are already familiar enough with linearity of expectation, when you hear the problem statement, you should be able to argue directly that, well, each of the sailors, I can treat them separately. Each of the sailors is contributing 1 over n to the final sum, because with probability 1 over n, they will be in their own cabin. And as there are n sailors, and each of them is contributing 1 over n, the expected value has to be 1. So if we were to run many experiments every day, you would not take note of how many sailors ended up in their cabin. The average of those values would be mathematically guaranteed to converge to exactly 1. Now, in some cases, the linearity of expectation is an obvious statement. If you roll 2 dice, then on each of them the expected value is the average. So this is 3.5. So the expected value of the roll of 2 dice is 7, right? That's not surprising. If you are rolling a 6-sided and a 10-sided die, you have an average of 3.5 on the smaller one, 5.5 on the bigger one. Together, the average is 9. if you do the math, if you write down all the combination of values, you will see that this is indeed true. But we will very soon encounter situations where the linearity of expectations will be used in less obvious settings. And one of the very nice settings in which we can encounter things like this is the following setting. So there is a very popular way of making parents buy more like cereal boxes and similar products for their children by adding some very small and cheap collectibles into those boxes. So, for example, we had there were albums with like football players, and you got a sticker with a football player with every box you purchased, and then you were trying to collect all of the stickers for the World Championships, so you had a full album, and this was really like everybody was crazy about it when we were little boys. And then the company benefited because they sold more boxes. Of course, this was then the secondary market when you were trying to swap the pictures you had doubles of with other people. And yeah, this has been done in the past many times with like some toys in the boxes and similar products. And it's actually a very interesting bit of maths, and there can be many different computational problems as well associated with it. So let's look at one specific setting that can be. So suppose there is 100 different stickers available. And each time you purchase a box, you are actually guaranteed to get a random sticker, all of them with equal probability. So there are no shenanigans like there will be different rarities of stickers or anything like that. We are assuming that everything is fair and square. Whenever you buy a box of the product, you will get one random sticker. So if you buy your first box, you will get your first sticker. If you buy the second box, you will get almost surely 2 different stickers. But if you are really, really unlucky in one of 100 cases, you will get 2 copies of the same sticker. If you buy 5 boxes, it is still much more likely that you will have 5 different stickers than any other scenario. Well, the other scenarios are possible, but less likely than that. If you buy 100 boxes, it is almost certain that you will not get 100 different stickers. You will have some duplicates. You will probably be somewhere about maybe 60, 70 stickers different and some duplicates. And now, assuming that you are shy or whatever, you are living in the middle of nowhere and there is nobody else for you to trade with, and the only way for you to acquire stickers is by actually buying more and more boxes of the product, what is the expected number of boxes you will need to purchase in order to have a full collection? So sometimes you can get really, really mathematically improbably lucky, and it will be just 100 boxes. Sometimes you may need 150 boxes to get all of the stickers. And if many people do the same thing, each of them writes down their own number of boxes they needed to purchase, what will be the average of all of those boxes? So what is the expected number of boxes we need to purchase? And again, before we actually do some calculations, shout out your guesses. So what is your intuition telling you? How many boxes on average will it take? Sorry?
300.
300.
2000.
2000, I heard? And log n. Okay, why is it the logarithm?
Linearity of
Yeah, exactly, linearity of expectation. Let's do the same thing as here. Let's do it with a single die. So we have a single die with faces numbered from 1 to 6. So there is 1, on the opposite side there is 6, there is 3, there is a 4, there is a 2, there is a 5, or swapped if you like the other symmetry better. And now we are going to roll it as many times as we have to until we see each of the faces at least once. So we want to roll at least, we will want to roll a 1, a 2, a 3, a 5, a 4, 5, and 6. Not necessarily in this order, but we need to see each of them come up For example, we are trying to make sure that the die isn't fully biased and doesn't avoid one of the faces completely. How many rolls will it take on average? And now you can view this as a process that has a state. Initially, we are in the state that we haven't seen anything. We make the first roll of the die, and we get to one of 6 possible states. To the state where we have seen a 1, to the state where we have seen a 2, and so on, or to the state when we have seen a 6. What happens in this state? We roll the die for a second time. With probability 1/6, we are staying in the exact same state. With probability 5/6, we are moving somewhere else. And again, with equal probability, it will be to one of the 5 states where we have seen a 1 and a 2, or a 1 and a 3, and so on. And from the 2, I can also, again, roll a 2 again, so stay here. I can roll a 1 in the second roll and go there, and so on. And now we can notice that the entire graph I started drawing here is symmetric. Why is this the case? Well, it's because we assume the die is symmetric, that is a fair die, that the probabilities are 1/6. So it doesn't matter what exact numbers I already rolled and what of them I didn't. The only thing that matters, we can break the symmetry by just keeping track of the count. So instead of having all of this branching, we can now say that we are in the state that we haven't seen any numbers. Now this is a 0, not an empty set. We make the first roll, and we can definitely get to the state that we have seen exactly one of the 6 numbers we are looking for. Now, what happens is that with probability 1/6, we will roll the same number we had before. And with probability 5/6, we will get to the state when we roll the second number, one that we haven't seen before. Now, as we are getting closer to the goal, in each roll it becomes more likely that we will see a number we have already seen, and less likely that we will get a new one. So from here, with probability 2/6, I'm getting a number I have already seen, and with probability 4/6, I'm getting the third new number. And we can continue on this way. So here it is equally likely, 3/6. It's an old number, 3/6. I'm getting the fourth number I haven't seen before. And with probability 4/6, I'm staying. And 2/6 is, so 4 numbers in this state, 4 numbers have already been seen, and 2 numbers are still the ones we are waiting for. So 2/6 is the probability that we will get one of those 2 good numbers we want to see. If that happens, we already have 5, and now with probability 5/6, I'm staying where I am, and with probability 1/6, I reach the final state when I have already seen all of the numbers. So now we are interested in the expected number of steps from here to there. The linearity of expectation is telling us that we can break this into the individual steps. So the expected value of the total number of steps is the expected number of steps from here to there, which is 1, plus the expected number of steps it takes to get from here to there, expected number of these steps, and so on. And now we can do this argument in general. And this is a very, again, it will be very simple, but it is a very, very powerful technique. So suppose we are repeating an experiment, and we are waiting for something to happen, and the probability that it will happen is p. What is the expected number of experiments we have to make until it happens? Yeah, 1/p. So intuitively, this should be obvious. Like if I'm rolling a die, and I want to see one specific number, the probability is 1/6, and it's reasonably intuitive that it should be exactly 6 attempts on average until I roll it. Now I will do the math, and I will show why this is the case. So we have 2 states. We have the state where we are at the beginning, where it still didn't happen, and each time we do an experiment, with probability p, it will happen, and with probability 1 - p, it doesn't happen. And here the important thing to realize is that the experiment doesn't have memory. The die doesn't have memory. The die doesn't remember what you rolled in the previous attempts. Each attempt is independent from the previous ones. So if it doesn't happen, we are back in the state from which we originally started. And now we know that the answer we seek, we can denote it x. So x is the expected number of attempts. And now the technique I'm going to show you is the technique of the first step. So let's look at what happens in the very first step of the experiment. So you made the experiment. So you made the experiment at least once, and this is guaranteed. And now, with probability p, you are done. Because with probability p, the thing you are waiting for happened, and now you will be doing no more experiments. So with probability p, you need 0 additional experiments. And with probability 1 minus p, in your first experiment, you failed. You are exactly where you started. And from this point, what is the number of steps you will need on average? Well, it's x. That's the definition of x. So you can write down this equation. The value x has to satisfy. The expected number of attempts is 1 that we will make at the very beginning. And with probability 1 minus p, we are back where we started. And from this state, we know that we need to make, on average, x additional experiments. And this is just a linear equation that is telling you that if you move this there, you get p times x equals 1. So x equals 1 over p. Yeah, again, this is a trick, but it's a very, very useful trick because it prevents you from doing the computations the hard way. So the hard way would be that you can express x also as follows, that with probability p, it happens already in the first attempt. So with probability p, the answer is 1. With probability 1 minus p, then times p, it happens in the second attempt. So in the first attempt we fail, in the second attempt we succeed. With this probability, the answer is 2. Then it is possible that we fail twice and then succeed, and the answer is 3. It is possible that we fail 3 times and then succeed, and the answer is 4. And this will give you a sum. The sum is solvable. You can do some operations on it and shift it by 1 and subtract it from itself, and you will essentially get this equation in the end anyways. So being able to think about expected values of processes with states in this way is very useful, and it can simplify your life considerably, and you don't have to do those sums manually. So what is this telling us for our problem? It is telling us that here we are waiting for the second number to appear. In each row, this happens with probability 5 over 6. So the expected number of tries we'll need is 1 over this, which is 6 over 5. So this is 1.2. So if we are waiting for anything other than a 6 to roll on the die, usually we will get it in the first attempt. Sometimes we will need 2 or 3 or more attempts. And the average number of attempts will come out to exactly 1.2. Now here the expected number of steps is 6 over 4. Here it is 6 over 3, 6 over 2, and 6 over 1. And if you want to have the formula pretty, this one can be written as 6 over 6. So for a regular 6-sided die, the total expected number of rolls until we see each of the values at least once is 6 times 1 over 6 plus 1 over 5 plus and so on plus 1 over 1. And the thing here in the brackets is called a harmonic number and is usually denoted like this, h with the index 6. So hn is the sum of 1 over 1 all the way through 1 over n. And we know that the nth harmonic number is very, very close to the natural logarithm of n. So this is the logarithm with base e of n. And they differ only by a constant. And you can show this essentially. If you know integrals, it's pretty obvious because the integral of the function 1 over I is exactly the natural logarithm. And if you are doing the discrete sum instead of the integral, then you have some imprecision with the boxes instead of the smooth curve. But the imprecision is only happening mostly at the beginning. At the end, the curve is almost straight, so the boxes are almost perfect. And yeah, there is not much of a difference anymore. So at the beginning, there starts to be a little bit of a difference, but after that, it doesn't really change So the nth harmonic number is approximately equal to ln n. If you are interested, you can add this up manually and see what it comes to for that. If you have here those 100 products, then the answer is exactly the same. You can do exactly the same math. So the first one will appear immediately. The second one afterwards, the expected number of items will be 100 over 100 over 99, then 100 over 98. And in the very end, when you already have 99 of the stickers and you are waiting for the last one in any specific box will appear with probability 1 over 100. So on average, you will need 100 boxes just for this last step of the game. So the expected number of boxes you will need to purchase is almost exactly n times natural logarithm of n. And for n equals 100, I think this comes up to something like 400, but feel free to check me with a calculator. And why this strategy is so popular in marketing is also an important thing to realize. And this is a property that is shared by very many games that have been used in the past to relieve people of their money. This is the psychological factor of you being very close to the goal. The reason why entire halls of pensioners are playing bingo every Sunday in the United Kingdom is exactly this property of bingo. That at the moment when somebody wins, almost everybody is close to winning. They are just missing these 1 or 2 pieces here and there. This trick with this selling stuff in boxes has the exact same property. You can start really quickly. The initial purchases, almost all of them will bring you closer to the goal. And the complexity is hidden at the very end. The last 2 stickers contributes 150 extra boxes. At the beginning, you get 10 stickers from 10 or 11 boxes, so it's much more rewarding. You are almost at the end, you almost have the complete collection. And yeah, there is a bit of a like sunk cost fallacy that you are not able to abandon the money you already put into this and you want to at least finish the collection, so you keep buying. And the only one that wins is the one who sells those boxes. All right, let's do one last thing before the break. We started talking about harmonic numbers. And harmonic numbers are actually a reasonably common thing to occur in time complexities of algorithms. So remembering this asymptotical behavior that the nth harmonic number is roughly log n can be useful also in algorithm analysis. Like personally, I would say that if you see a log n in time complexity, the most common source is the use of a like ordered data structure. The second most common source would be some kind of a divide and conquer of the like merge sort type. So if you have the recursion tree, you have the same amount of total work done on each level of the recursion tree, and then you get the logarithm as the number of those layers of the recursion tree. So this is one of the branches of the master theorem for those of you that have already seen it. And then, yeah, maybe the third most common source of logarithms somewhere in time complexities could be these harmonic numbers. One of the very famous old puzzles where harmonic numbers did come up and then they didn't is the puzzle with the bricks. So suppose you have a table, and now you have a brick. A brick is essentially, let's do it in 2D. So a brick is a rectangle, and you want to push the brick to hang over the side of the table. If you have a single brick, then it is obvious that you can push the brick at most halfway from the table. So the brick has a center of mass. The center of mass is in the center of the brick. And as long as the center of mass is on the table, the brick will remain stable. When it reaches the edge, there is this like one unstable location where the epsilon matters. And then when you push it farther on, then now the center of mass is already beyond the edge of the table, and now you have force going like this, and the force has a segment that goes like this, and it will cause the brick to rotate and fall off the table. So if you have just a single brick, the farthest away you can get beyond the edge of the table is half a brick. what happens if you have two bricks? If you have two bricks and place them one on top of the other, the top brick can reach halfway over the edge of the bottom brick. So if the center of mass of the top brick is still here or to the left, then the top brick doesn't fall from the bottom one. And as long as this configuration is stable, we can now view it as a single object. The center of mass of this single object is here, halfway between the centers of masses of those two bricks. And as long as this center of mass isn't beyond the edge of the table, the collection, this object built of two bricks will stay stable on top of the table. So here it is 1/2 of a brick and 1/4 of a brick. And we can now continue in the very same fashion. So now, assuming this configuration of bricks is stable, you can, instead of directly placing it on a table, we can place it onto a third brick, like this. And now, after having 1/2 a brick and 1/4 of a brick, if you now find the center of mass of this entire thing, and you see where you can place the table, you will get 1/6 of a brick over here. So if you have a stable configuration of these three bricks, you can still push it a little bit behind the edge of the table. And if you will continue building the bricks like this, so what you will get will look as follows. Eventually it will, so these distances will shorten and it will be even closer to this one. But here will be 1/2, 4, 6, 8, 10, 12, and so on. And you will get half of the harmonic number as the overhang with n bricks. So what this is showing you is that as the number of bricks grows to infinity, you can get arbitrarily far beyond the edge of the table, but very, very slowly. Logarithm is growing very slowly, so the binary logarithm of 10 to the 9, which is a billion, is approximately 30 only, and the natural logarithm is even smaller than that. So in order to get several bricks beyond the edge of the table, it will take you a lot of bricks. But like in theory, it is possible. So, and for many, many years, it was thought that asymptotically you couldn't do anything better like this. But then some people with a lot of time on their hands actually did come up with significantly better constructions. And I believe that it is now actually also with a proven upper bound. But at least I'm 100% sure that there is a lower bound of not logarithm of n, but n to the power of 1/3. So this is the cube root of n. So there is a different construction of bricks where you do something like there is a bit of bricks that overhangs, and then there is a huge block of bricks here as a counterweight. And the length by which you can reach beyond the edge of the table is actually some small power of n instead of just the logarithm. So this is a function that still grows slowly, but much, much asymptotically faster than the logarithm. I will put a link to this specific construction into the materials section of the website of the grader, so you can look at the pictures yourselves afterwards. Okay, looks like we still have a bit of time until the coffee break is ready for us, so I'll just continue talking about other stuff and then make a break at some appropriate point. So let's get to some slightly more difficult stuff now. Okay, so you have probably encountered binary trees. I hope everybody here has seen them. And you can use them as a data structure, as a binary search tree, by maintaining order inside the tree. So you want to have the property that if there is a value x in the root of the tree, there are values less than x in the left subtree and the values greater than x in the right subtree. If this property is satisfied in each and every vertex of the binary tree, then it is a binary search tree, which means that you can efficiently search for elements by starting at the root. And in each step, either you find it or you know which path to choose. So you just go down from the root until you find the element. So I say efficient, but the efficiency actually depends on the shape of the tree. And as we know, if you are just inserting the values into a binary search tree as they come, you will usually get a nice balanced tree, but there are some corner cases, and the worst case behavior can be pretty bad. The worst case behavior can be that you will obtain a tree that is nowhere near balanced, that is actually just a single line going from the top to the bottom, and it doesn't save you any time in the lookups in comparison to an ordinary array. And you don't just have to have a single line that goes like this or like that, but it is also possible that you have something like there is an 8 in the root, and then there is a child, only the left child with a 1, and then there is only the right child with a 2, and then there is only the right child with a 7, and then only the left child with a 3, and so on. So this is also one possible way in which the binary search tree can be degenerate. If you are inserting the values in this specific order, that is always the smallest or the largest of the remaining ones, you will get a line. And therefore, there are some more complicated data structures that are on top of the basic idea of binary search trees. They are trying to do some kind of balancing. And those can be more complicated. We'll get to a few of them later in the lecture. But for now, let's stay with a much more simpler observation. So if we had an enemy choosing the order in which you are inserting the values into the search tree, then they can force us to have some degenerate search trees. But what happens in the much nicer case when the order in which the elements appear and they are inserted into the tree is actually random? And intuition is telling us that with high probability we should get a tree that looks nice. Right? If there is no enemy playing around and nobody forcing us to have some very specific bad orders, it should be the case that the trees will be nice and shallow. So now the question I'm asking you is as follows. Suppose you have a random permutation of values 1 through n. And now you are going to use this permutation to build a binary search tree. So you are inserting these values. So you will start with an empty binary search tree, and you will be just doing the very standard basic insert in the order in which they are shuffled in the permutation. We are using numbers 1 through n, but this is just for simplicity of the analysis. So this is essentially any setting where the elements that are actually being put into the tree are appearing in a random order. The 1 through n just represents to the actual order of those elements in the final sorted order when everything is already inserted into the tree. So we have these numbers 1 through n. We are going to insert them into the tree. And I'm asking you, what is the expected time complexity of building the entire tree this way? How can we answer such a question? And this is where our preparations with the linearity of expectation will become very, very useful really quickly. So what happens during the building of such a tree? You are comparing some elements. This is what takes essentially the entire time complexity. You are inserting the first element, it goes directly to the root, we are done. For the second element, you compare it to the first one, and it goes either, it becomes the root of the left subtree, or it becomes the root of the right subtree, and so on. So each element you are inserting, you are comparing to some of the elements, you are going down the tree until you find the exact location for this element. So there is a constant amount of work done per each element when you are actually creating its node in the tree. And the rest of the work during the entire building of the tree is simply those comparisons. The constant work per node is just linear time. So the number of comparisons is what we are asking for. So the expected time complexity asymptotically is the same thing as the expected number of comparisons. And how can we express this expected number of comparisons? Let's have, again, what is called indicator variables. So for each pair of values, I and j, I is less than j, we will have one single variable that is telling us whether at some point during the building of a tree, we actually compared the value I and the value j. So this variable is either 1 or 0. 1 it is if we compared I and j, and 0 if we didn't. And now the total expected number of comparisons is the expected value of the sum of all xij. And this is, by linearity of expectation, sum of the expected values of xij. And this is therefore the sum of the probabilities that I will compare the value I and j over all pairs of I and j. So the expected number of comparisons can be computed by looking at each pair of numbers, computing the probability that these two numbers will be compared to each other while building the tree, and then summing up all of those probabilities. So this is what we are going to do now, and this will be the last thing we do before the break. So let's start with considering two numbers that follow each other in the order, so a 7 and an 8. As you are building the tree, you are picking some other numbers, you are inserting them into the tree, and then at some point you will pick one of these two numbers. Let's say it's the 7. So we already have some kind of a tree. It's not necessarily perfectly balanced. This is what we got from those random choices so far. And now we have chosen the 7, and now we have inserted the 7 into the tree, and it went there. Now the important observation is that as 7 and 8 are immediately after each other, if we had chosen 8 at this moment in time instead of the 7, it would have ended up in the exact same spot, right? So now the process continues. We are choosing again some different numbers. We are inserting them into the tree. We are creating more nodes. We may create nodes also as well here. And now later, we'll choose the second of these two numbers. In our example, it is the 8. And regardless of what happened in between, the path where we inserted the 7 is still there. And when we will be now inserting the 8, we have to follow the exact same path until here. And we have to compare the 7 and the 8. And then the 8 will be inserted into this subtree. And as is the next smallest value, it will be inserted as the leftmost element in the...
It's greater.
See? Yeah, it's greater than 7, sorry. So it goes into the right subtree of 7, and there it will be the minimum. Yes, you're right. Thank you. So the 7 and the 8, and in general each pair of consecutive numbers, will definitely be compared. And this is actually a necessity, because when you have the final binary search tree constructed, it actually carries enough information about the entire sorted order of all of the elements that are inside it. This is really easy to see because you just do the in-order traversal of the tree, and the in-order traversal is the sorted order of all of those elements. So the tree had to do all the comparisons during the insertion to be sure of the order of elements. And in order to be sure about the order of all elements, you need to compare each pair of consecutive elements at some point in time. So yeah, this is a nice sanity check that we are getting reasonably outcomes. So the 7 and the 8 have to be compared, and each pair of consecutive elements has to be compared. So xi and I plus 1 is always 1. And now, what happens in a more general case? So suppose we have a 7 and a 9. Let's stay again with the example. And now there is a value 8 in between those two. And again, as before, we can look at what's going on before any of these three numbers appear. So at this point in time, again, we have some general tree. We have already inserted some elements. And now we will be inserting the first one of these three values. It can be the 7, it can be the 8, it can be the 9. By symmetry, all of these happen with the same probability. If we insert the 7, or if we insert the 9 at this moment in time, we get the exact same situation as before. So if now we insert the 7, this path will already be there. And as at this particular moment, the 8 and the 9, which are a block of consecutive values, would go down the tree the same way. Later on, when we are inserting the 8, it will pass through this path. And later on, more importantly, when we are inserting the 9, it will go down this path, and it will meet the 7, and we will actually compare them. But on the other hand, if at this moment in time we insert the 8 into the tree, what will happen in the future is when we will be inserting the 7, it will go down this path and then to the left, and the 7 will end up in somewhere in this subtree. When inserting the 9, it will go down this path, and then it will go right, and end up somewhere in the other subtree of the 8. So if we insert the 8 before either of the numbers 7 and 9, then it will actually separate them already, and we will never compare the 7 and 9 directly to each other. So the probability that 7 and 9 will be compared is 2/3. So if we insert 7 first out of those three, they will get compared. If we insert 9 first, they will get compared. But if we insert 8 first, they will not get compared. So the probability that I and I plus 2 get compared is 2/3. And now it should be obvious how to generalize this. So if we are asking the question, what is the probability that 7 and 10 will be compared to each other during the building of the binary search tree? It happens if and only if, from the numbers 7, 8, 9, 10, the first one inserted is either the 7 or the 10. If this happens, then they will meet each other during the construction. If anything in between them is inserted before, then it will split them into different subtrees and they will not be compared to each other. So the general formula then is X, the probability that I and I plus K will be compared is 2 over, what is it, K plus 1. Yes, so this range has K plus 1 numbers, and if either of the edges of the range is the first one inserted, then we will get the comparison. In all other cases, we will not get the comparison. So we did the math. We can reward ourselves with the coffee break. After the coffee break, we will finish summing this up and seeing what the expected time actually is.
do all kinds of variations of my name, and I don't really mind. Embrace you
witness something very quickly. For most of the remaining contests, I will probably not be there physically because it doesn't really make sense, but I would still want to be available for you to ask questions. And I wanted just to check if, for example, is Discord fine for this. So I am on Discord. I have it also on my cell phone. Will it be okay for you to just send me a DM there if you want to ask questions, or do you want to use some other platform? Telegram is also okay. Yeah. So I can publish also my Telegram handle. Feel free to use either of those. I love the modern times because, like back in the day when you traveled to a different country where you didn't speak the language, it was kind of hard to even get around. Even if you already had some like a match, you needed to make. Okay, are we ready to start the second half? Okay, so welcome back everybody. Let's do some more math on these random trees and let's see what happens. Before we get to doing the actual math, I was too lazy with the notation, so let me correct what I have written here on the board. These numbers are not the values of these random variables. These numbers are the expected values of those random variables. That's the proper notation. So in other words, these numbers are the probabilities that these things happen, that these items do get compared. So this is now the sum we are trying to evaluate. So the total running time of building this random binary search tree is proportional to the sum of these probabilities. So in other words, to the expected number of comparisons between elements that are done while the tree is being constructed. So what is this? How can we compute this? So let's imagine all of these values. Pij we are trying to sum inside the table. So this is I, this is j. I can be 1, 2, 3, 4, 5, and so on. J can be only from 2, 3, 4, 5, 6, 7. And inside the table, we get a collection of ones. Here, close to the diagonal. So 5 and 6 will be compared with probability 1, and so on. Here it will be 2 over 3, 2 over 4, 2 over 5, 2 over 6, 2 over 7. The farther away the two numbers are, the less likely it is that they will actually be compared while building the tree. So everywhere on this diagonal we get 2 over 3. This is the distance 2. Everywhere on this diagonal we get 2 over 4. Everywhere on this diagonal we get 2 over 5. And so on. And so now there is an entire triangle on the board, and the sum of values in this triangle is proportional to the time complexity. So the sum of all of these fractions is the total expected number of comparisons. What you can do now is you can visualize this one as 2 over 2 because this is what it is. There are two consecutive elements and one of those will be selected. So 2 are good ones, 2 is the total. So this makes the row looks nicer. And now we can argue as follows. So for an upper bound on the sum of this entire triangle, we can just look at the first row. And the first row is 2 over 2 plus 2 over 3 plus all the way 2 through 2 over n. So this is twice hn and minus 1 because at the beginning we don't have 2 over 1, so there is one term we are missing. So this is less than 2 times Hn. And each of the other rows is the same sum, but one term shorter. So for an upper bound, we can say that the sum of the entire table, this entire value, let's call it capital A, we can say that A is less than or equal to n times sum of the biggest row, and the sum of the biggest row is 2 times Hn, and therefore A is proportional to n times is less than or equal to, and n is O of n log n. It is at most on the order of n times log n. If you want a corresponding lower bound, you can note that if you sum up just the first half of the table, you will get not twice Hn, but you will get twice Hn half. And Hn half is roughly the logarithm of n half, which is the logarithm of n minus the logarithm of 2, and this is just a constant, so again we can ignore the constant. So asymptotically, the sum of the first half of this row is roughly log n, and we have at least n half of such copies. So we have n half times the logarithm of n half as a subset of our table, so also lower bound can be shown to be n log n. So by estimating the sum of this table of fractions from above, we get that it is asymptotically at most n log n. By taking a subset of the table and summing it, we get that it is asymptotically at least n log n, and so this is also a capital theta, so this is an asymptotically exact estimate. So if you take a random permutation of n elements and you use them to build a binary search tree, the time complexity of the entire process will be just n log n on average. And if you are the one in control of shuffling the elements, or if you are guaranteed that the elements will actually appear in random order, then there is no bad input. So this is the expected running time in the sense that there are no specific bad inputs. There is no enemy that can force you to have a big time complexity. You can be unlucky and have a single run of your program run longer than another. But again, we can show that if we do the math more properly, we can show that this is not just the average, but that the average, or somewhere around the average, will happen with high probability. So it is very, very unlikely to be unlucky many times in a row and get a tree that is not balanced and that takes a long time to construct. Okay, are we happy with this result? Do we understand it? And does it make sense? Yeah, this is an important checkpoint because we are not stopping here. We are going to use this as an observation for other things now. So right now, with this observation, we have not just realized that only specific corner cases are our enemy when building random trees. Let's look at a different setting, but we will see very quickly that it is essentially the same setting, and this is quicksort. Again, there are various flavors of quicksort, there are various technical details that can differ between different implementations. So we will choose one specific one that will have the property of very closely resembling what we just saw. So suppose, for simplicity, that what we are sorting is an array with n distinct elements. This is essentially the worst case for most sorting algorithms because you don't have anything where you can save time. If you are sorting n equal elements, there are some algorithms that will have a special case or that will behave on this array in such a way that they will finish in linear time. In fact, it is also possible to implement quicksort in such a way. So in quicksort, the main step is called the pivotization. So what's going on in this process is that you have a sub-array you are currently sorting. Using some strategy, you pick one of those elements or one value arbitrarily as a pivot, and then you split the array into 2 or 3 segments. And one option you have is to split the array into exactly 3 segments. So if you have the value p as a pivot, then you split the array into elements that are less than p, equal to p, and greater than p. Once you do this, you already know that these elements are in their proper places, and then you recursively have to sort the smaller ones, and recursively have to sort the bigger ones, so you make 2 recursive calls, and those will rearrange these elements and those elements. If you are using this particular flavor of quicksort, if you have all of the elements equal, you pick one of them as the pivot, you will get the segment of values of equal to p, and the entire array will be sorted in linear time. So, for the analysis, we will now assume that we are picking one of the elements as the pivot from the range, uniformly at random in each step, and we will assume that all of the elements are distinct. So we will get just a single pivot in its proper place, and then there will be some elements to the left and to the right of it. And now we are asking again, the same question we were asking the previous case. What is the expected time complexity of this particular flavor of quicksort? And you can now observe that, again, what is the source of the time complexity of an implementation of quicksort like this? We can do the pivotization very, very easily with using several vectors. So we will use a vector for elements that are less than p, a vector for elements that are equal to p, or just if we are guaranteed that there are no duplicates, then we can use just a single variable, and another empty vector for elements greater than p. And once we have chosen the pivot in this segment of an array, we can go through all of the elements in this array, compare each of them to the pivot, and place it into the appropriate array. So this one goes to the bin of the smaller ones, this one goes into the bin of the bigger ones, and then we just concatenate those arrays. So we put the smaller element first, then the equal one, and the bigger elements, and we are done. So the time needed to process this segment, if we are not counting the recursive calls, is proportional to the length of the segment, or equivalently, and this is now the interesting thing for us, the time complexity of this particular step of quicksort is proportional to the number of comparisons that are done during this step. We are comparing the pivot to all of the other elements in this range. And now hopefully some of you are already starting to see the similarities between this and the previous setup. So suppose we are sorting again, just for simplicity, imagine that the values we are sorting are actually the values 1 through n. The sorting algorithm doesn't know about this. The sorting algorithm just performs the general procedure it is always performing. But we know this, and we are using this in our analysis. And again, we can ask about the probabilities p, I, j. What is the probability that at any point during this running time, the quicksort will actually compare the element I and the element j? And the answer will turn out to be remarkably similar. Why? Because as long as both of the values I and j fall into the same segment of the array, so we are doing some pivotization steps, and in those pivotization steps, the pivot is chosen somewhere outside of the range between I and j, and both of them are compared to the pivot, and both of them end up on the same side. And then, at some moment, we have an array, and within the array, one of the values between I and j will get chosen as the next pivot. And if this happens to be the value I, or if this happens to be the value j, then as a pivot it will be compared to the other one among them. And if any of the values in between is chosen as a pivot sooner than I or j in this particular branch of the quicksort, if any of these is chosen as a pivot, then we will compare it to I, we will compare it to j, I will end up in the left half, j will end up in the right half, there will be different recursive calls for both of them, and they will not get compared. So again, the probability that I and j will get compared to each other is exactly 2 over j minus I and plus 1. Yeah, because like each of these numbers is in each step equally likely to be chosen as a pivot. If none of them are, then we just do the same argument in the following step. If one of them is chosen as the next pivot, and we are choosing the pivot uniformly at random, then it is guaranteed that the probabilities for each of them being chosen are exactly the same. So the probability that this or this is chosen and not anything in between them is exactly this value. So we get exactly the same variables we got in the previous solution, and therefore we are very happy because we don't have to do the estimates of sums again, and we can immediately conclude that using exactly the same math, the same reasoning, we can conclude that the time complexity of randomized quicksort when you are selecting the pivot at random is actually n times log n. And it still doesn't have to stop there. And now we are going to the very last application of this particular observation, and these are trees. Okay, so what's going on here? If you are doing these programming competitions, there comes a time where you are forced to implement your own binary search tree. Why? Well, because the tasks, if you get to a suitable level of difficulty, they will require not just using the search tree for storage and lookup of elements, but they will require you to do some kind of more complicated operations of them on those values. There are already some things implemented within these standards, like STL distributed with G++ and so on, where you have like policy-based data structures, and you can declare, if you know the magic words, you can declare your own binary search tree, or for example a set or a map that also has for some basic stuff like order statistics, so you can efficiently find the smallest element in the tree, or index into the tree, or do the reverse operation. So take an element that is stored inside the set and ask for its index. So what is the number of this element if they are numbered from the smallest one to the largest one. But there can be even more complicated operations. At some point, you need to do your own implementation of a tree and maintain this information propagated along the tree. So usually for the leaf, it is obvious what the information is, and then you have some way of recomputing the information. If you know it about the left subtree and your right subtree and yourself, you can use this to recompute the information about the entire tree where you are the root. And if you know how to do this for any kind of a property, you can then maintain this information as you are modifying your tree. So if you are adding new elements, if you are removing elements, each time you restructure the tree, you only need to recompute the information along the places where you actually modified the tree, and this will make maintaining the information easy. And there used to be years in the history of programming competitions where this was considered unfeasible, and nobody would set a problem like this, except maybe for like long-term competitions. If the contestants are at home and have a month and they are really good, then yes, we can ask them to set them a problem that will essentially require them to implement their own trees, because they can use references and spend time debugging. But yeah, for a long, long time, this was something that was not considered feasible, and people didn't set such problems. And then slowly people started playing around with implementations of various flavors of these balanced search trees, and they came to a realization that a few of them are actually within the human possibilities to be implemented, not just with a 10-page reference, but off the top of one's head. At the moment, I think I'm able to code like maybe 4 or 5 different such structures, but I do have my preferences among them as well, which ones are easier or harder to implement, and also like some of them may be better suitable for some tasks or other tasks. So there can be stuff like you may need to merge different trees together and trees of different sizes and do other kinds of operations. So yeah, it still pays off to have a wider repository, but definitely a good first step, if you are not there yet, is learning at least one
balanced search tree you can implement from scratch. And trips are one of the current best starting points. It turns out to be the case that the popular modern implementation, most top competitive contestants programmers use for implementation of trips is something that was actually known already by the authors of the very first paper. So in the very first paper there is already a footnote mentioning that instead of doing this you can do that, and it is simpler. But it is actually the case that many of the other tricks in these simple implementations of data structures were actually first invented by people from this programming contest community, simply because they're spending so much time on it and trying around different ways of doing stuff. So trips, as I was saying, are one of the currently simplest guaranteed balanced binary trees, or guaranteed at least in the randomized sense with high probability. So for the benefit of those who haven't seen this before, I will go through everything from scratch. I will explain what they are, and then I will show you both an argument about why they are efficient and why you can rely on them, and also some bits about how they should be implemented easily. So what we are going to do now is one more time we are going to insert elements into a binary search tree, but this time we want to somehow make sure that the search tree will not be degenerate. We would like to prevent these pathological cases from happening, and we will do it in the following way. So instead of just inserting the elements we want to insert, we will be having a tree that is storing a pair of values within each node. Within each node you will have the element itself, and you will have a number that we can call, for example, priority. And the priority is, the simplest way you can imagine for them is that they are random numbers between 0 and 1. So these are real numbers, all of them. We will, for simplicity, we'll assume that the range of the randoms is such that all of them are distinct, and if two of them are equal, we don't really care what happens, that their tie can be broken randomly. So for the sake of analysis, assume that these are random numbers from this range, and that with probability 1, all of them are distinct, so we don't have to care about the equality there. And now we will have an entire tree full of records like this. And the tree will satisfy two properties at the same time. When we are looking only at the keys, only at the values x that we are actually storing in the tree, it will still be a binary search tree. So this one will be smaller than that one, this one will be smaller than that one. So if we ignore the priorities and look only at the keys that are actually stored in the tree, it is still a binary search tree. We can do all kinds of stuff with a normal BST. What's the purpose of the priorities? If we only look at the priorities themselves, the requirement will be that this must be a heap. And let's say this is a maximum heap. So the value in the root has to always be greater than the values in both of the children. And this has to be true also in all of the possible subtrees. So if you are looking at the keys only, it is a BST, it is a tree. If you are looking at the priorities only, it is a heap. And the name tree is a portmanteau of these two words, so it is a tree. So we have these requirements, but do they make sense? What's going on here? So let's suppose that instead of showing you an actual tree, those properties are already satisfied, I will just give you the collection of records. So you have x1 and p1, you have x2 and p2, and so on, xn and pn. So you have these individual records, and I will now ask you to build the tree. Is it always possible? How many ways are there to do it? And the answer is yes, it is always possible. And if the priorities are indeed unique, there is exactly one way always to do it. What it is? So Remember that the priorities have to form a heap. So if you look at the maximum of all the priorities in the entire collection, the maximum has to end up in the root. So we can find the largest value among all of these priorities, and this particular record will become the root of the entire tree. Now we can look at the other property. If we have the keys, it has to be a search tree. So as soon as we know that the value xi with the priority pi is in the root, all of the values that have a smaller key than xi have to go into the left subtree, and all of the values with a bigger value of the key have to go into the right subtree. So now we have a collection of items here and a collection of items there. And now we can proceed recursively repeating the same two arguments alternately. So among these, which one will be the root of this subtree? Well, the one with the highest priority among all of them. So here we find the largest priority, this will be the next root, and then the rest will be distributed there. Here we do the exact same thing. And now, so what is going on here? We have now shown that if all of the priorities are distinct, the shape of the tree is always uniquely determined by those priorities. So if you have the same collection of keys, but you generate different set of priorities, you will get a different shape of the resulting tree. In particular, the maximum priority is choosing the root of the tree. And what's going on there? So the situation when we are generating the priorities for the values, the situation is completely symmetric. So if we are asking about the probability that this particular element will get the maximum probability, the probability is always 1 over n. There are n elements, each of them is equally likely to end up with the maximum priority. So we are choosing the element to, as if insert first into the tree, uniformly at random when we are generating the initial probabilities. And we can now repeat the same argument again for the subtrees. So we can now forget about the right subtree, focus on only on the left one. Among the values that ended up in the left subtree, again, it is perfectly symmetric. So each of them is equally likely to be the one that among them has the biggest priority. And this value will then be the one that will be the root of this subtree. And then we again proceed with the same argument for the subtrees afterwards. So in some sense, the final tree will then correspond to a randomly chosen binary search tree for the initial keys x1 through xn. In other words, if you took these records, if you sorted them by priority from the biggest to the smallest, and then used this order to insert them into the empty binary search tree, what you will end up with at the very end will be exactly the tree that was chosen at random by selecting these priorities. So for the third time in a row, we have a very similar setting, that we have chosen a random permutation of these nodes by assigning them the priorities. And then when we build the tree, it will be a randomly selected binary tree among all of the possible ones. And now we know that the pathological ones that are very deep and take a long time to construct, they are very unlikely to happen. And by selecting the shape of the tree at random in this way, we are almost guaranteed, that, or more precisely with high probability we know, that the shape of the tree will be reasonably balanced, and if we were actually to insert the elements one at a time, the total time spent on inserting all of those elements will be, with high probability, just on the order of n times log n. So this is the main trick, and the big conceptual difference between this and the original example when we first had to randomly permute the elements and then had to insert them into the tree is that this trick with the random priorities is allowing us to do this dynamically as well. So we don't have to just have all of the elements available at the beginning, but we can use the tree as a fully functional data structure. We can insert elements during the run of the program, erase some elements, insert new elements, and so on. The content of the tree can change over time. And then at any moment in time, we can like freeze the situation, look at the snapshot, and about this particular snapshot, we can always make the same argument that with high probability at this particular moment, the tree has to be balanced because we just use the random priorities that are currently assigned to the current values stored inside the tree to choose essentially the shape of the tree at random. So this is the intuition behind why the trees will almost certainly operate in the as optimal time complexity of k operations taking k times log n time. Okay, does the argument make sense? If yes, then let's take a closer look at the implementation. Yes?
So the argument is that constructing the tree is n log n, but does this also guarantee that the height is log n as well?
This particular argument, I don't think it's straightforward does, but yeah, there is, you can do more math on this and show that on the screen. So it is true, it just doesn't follow from this particular argument, and it is not as nice, or at least I cannot do it as nicely.
Como de poner prioridades y es randomizado, pues casi que seguro en orden en vez de lineal.
Okay, so we would like to use the strips as a data structure, and as a first step we would like to implement the functionality of inserting a new element into the tree and erasing an element into the tree. So yeah, those of you who have already implemented at least one tree or read about them know that now comes a twist. We are not going to do that. We are going to do two completely different operations that are really easy to implement, and then we'll use those as a building stone to do the rest. And the operations will look as follows. These will be operations split and merge. The operation split is doing the following. You already have a tree in memory, and you will choose a value x that is a threshold, and now you will split the tree into two smaller trees. So this will be editing the tree directly in memory. You will start with a single tree and a pointer to its root as the input, and you will end up with two separate smaller trees that will be obtained by cutting the original tree into two halves. The first half will have the elements with the keys less than or equal to the x you chose, and the other one will have elements greater than x. How do we implement such a split? So let's call this x with an index t as the threshold. And the implementation looks as follows. So we have the tree, we look at the root. There is a value x, and with xi with some priority pi. And there are like only two cases, and they are essentially symmetric, because so either this xi is less than or equal to the threshold, so it belongs to the left, or it is greater than threshold and it belongs to the right. So without loss of generality, suppose this belongs to the left, what can we tell then? This entire left subtree of the tree, also all of them are values that are less than this one, so they all belong to the left. And on the right, what we need to do is we need to take the right subtree, and now we need to call exactly the same thing on it recursively, so we need to split it according to the same threshold xt. And once the recursive call finishes, and we will get two separate trees from the right subtree, this one will be the right tree, this is the right answer finally, and what we have got left here will be the subtree of this one. So just make the same recursive call on the correct subtree, and then one of the returned smaller trees will still remain in the left half, and the other one will be the right half, and that's it. So this is just one pass from the top to the bottom. You split the tree with memory, and you return. One of the returned values will be the pointer to the original root. This will be, in this case, the left subtree, in the symmetric case, the right subtree, and the other one will be the pointer to the root of the one where we actually made the split. So split is really easy to implement in linear time. This is just one pass from the top to the bottom. And now merge is the exact opposite of the operation. So merge is undo a split. So for merge, what you have are two trees. And it is, if you look at the keys, the biggest key in this one is smaller than the smallest key in that one. So all of these elements belong to the left of all of those elements. How do you do the merge? Well, again, recursively. You look at the roots of both of the subtrees, and this time you compare the priorities. Which one should be the root of the merged tree? The one with the bigger priority out of those two. So suppose it is this one. So if it is this one, this will be the root of the new tree. What will be the right subtree? Well, the right subtree will be the right subtree it currently has. So these are the values that are bigger than the key here. And for the left subtree, we have the values that are smaller than the key. And this is one such collection of items. And the left subtree here is the second such collection of items. So in order to produce the left subtree of the merged of those two trees, we just need to merge this and this. So we started with the call merge this tree and this tree. We did one if, and after that if, we do one recursive call in order to get the new left subtree, merge this tree and this tree. So again, it is just one pass from the top to the bottom, making one recursive call until we get to a leaf when we just merge something with an empty tree and then we get the something. So this is really easy to do in all of depth of the tree. This is really easy to do in all of depth of the tree. And yeah, it can be shown that, again, with high likelihood asymptotically, the depth of the tree is log n. So these are both in logarithmic time with high probability. And now if you can do a split and you can do a merge, then you can very easily do insert and you can very easily do erase. How do you erase? You can take the entire tree, and if you want to erase x, you first split it into less than or equal x and greater than x, and then you take this part and you split it into less than or equal to x minus 1, and the rest will be a tree containing exactly the x, and here you have still left over the greater than x, and now you just discard this and merge those two back together. And if you want to insert an element, you can do exactly the same thing. You can then make sure that the element is not there already, and if it's not there, then you will create this one and merge it together twice. So again, this gives you a very simple implementation, logarithmic time complexity, and this is something you should be able to do with some, like the first time you will try to implement this, it will be a bit of pain with debugging where your pointers are going and being really careful about it. But yeah, it is something that you should eventually be able to debug, and once you learn the technicalities, or there are like reference implementations available online. I will give you again into the materials a link to one such implementation. You can study those, and this is something that, yeah, I'm reasonably confident that on any day I can sit down and reproduce this also in actual working code, because the idea of this is not that complicated. Like the original implementations of actual balanced trees were pretty crazy. If you look at, like if you open the sources of STL that is distributed with your G++, you will see that the standard implementation of sets and maps is using like the canonical version of red-black trees. And there is like pages and pages of cases handling, like if I'm black with a red subchild, or what I should do with in terms of like rotations of the tree to balance it. And yeah, well, I did at some point exactly once, I think, re-implement my own version of red-black trees. It's not something I can do from the top of my head, and it's definitely not something I find pleasant. And this version is much more user-friendly. So in many cases, like if you are forced into implementing your own binary search trees, this is probably the way to go. And also for like maybe like code libraries for ICPC, it is possible to compress the implementation of trees, each of these methods, split, merge, insert, erase, to just very few lines of code, and this makes it really nice for the settings where you need to transcribe it from paper. Okay, so this is it. We still have a bit of time left, so I can talk about modifications of these trees in more detail. So again, this is a technique that you can use for any kind of a search tree, essentially, as long as you are doing only some local modifications with it. And I will show you like the basic thing you can do with it to add some more information. And the new information we will be adding will be that if you have the tree, then in every node you can remember all kinds of aggregate information about the subtree where you are in. And the easiest such information you can have is the size of the subtree. So each leaf will remember the value 1, and each inner node will remember or recompute whenever it is needed the value of the, if you look into the left child and see that each size of the subtree is 1, the right child has a subtree of size 1, so my entire tree has a size of 1 plus myself, and this is 3. This one will see that my left child has a subtree of size 1, there is no right child, there is myself, so my tree has size 2. This one will see that my size is 3, this one will see that my size is 7. What is the use of this information? As soon as we have this information as extra in our tree, we can use the tree to answer new types of queries. So for example, if you want the second smallest value, how do you find the second smallest value? So we start at the root, we look into the left child. The left child is a subtree of size 3, so the second smallest value is definitely there. Now we are here, we want still the second smallest value. The left child is of size 1, so that is the smallest value, and therefore the second smallest value is this here, and we can return it. If we want the fifth smallest value, what do we do? We start at the root. The left child has size 3, so these are the first, second, and third smallest. Those are not the ones we want. This one is the fourth smallest. This is not the one we want. So we make a recursive call. Out of this subtree, I want the smallest, the first one, because I already saw 3 plus 1, 4, and I want the fifth one. So now I'm in this subtree, and I was the first smallest. And this entire step was done in constant time. So as I'm going down the tree, in each vertex, in constant time, I can re-evaluate whether it is him, whether it is in the left subtree, whether it's in the right subtree, and if it is in the right subtree, I can also modify the index I'm looking for. So I can, in logarithmic time, or general in time proportional to depth of the tree, I can go from the index to the value. So we are storing the sorted set of these elements, and we can also take any index into the set and convert it into an appropriate value. And we can also do the same thing in the reverse. What is the ordinal number within the set of this particular node? In order to get this ordinal number, this will be 1 plus the number of elements smaller than it. Where are the elements smaller than it? Some of them are in its left subtree. We know how many of them there are. We can go up. We came up from the left subtree, so we don't care. Now we came up from the right subtree, so everybody here is smaller than us. There's 3 of them. And also the root is smaller than us. There is 1 of them. And that way we could convert this into the number. So as we were going up the tree this time, we were counting that here we saw 1 smaller element, here we saw 3 and 1, so we saw 5 smaller elements. This one is the 6th in the size order. So in logarithmic time, you can go from index to the value. In logarithmic time, you can go from the value to the index. This can be pretty useful. You can store all kinds of other aggregate stuff, aggregate information about your subtrees, and use it to answer all kinds of these other queries. And the important property of doing this for your own implementation of a data structure, such a tree, is that this value, like, it is easy if you can recompute, if you can compute it once at the beginning and then reuse it. But if your set is changing over time, so if the new elements are appearing and disappearing, so you are inserting, erasing elements, and then in between those operations, you need to answer the queries of these other types. What is going on is that you need to maintain this information about your tree as the tree is changing. And this is where it is good to have an implementation of a tree, where all of the changes made to the shape of the tree are in some sense local. So for example, if we are splitting a tree into 2, what's happening is that in the original tree, we are essentially going recursively down one of the paths that is like exactly following the split between the small values and the large values, and we are splitting the tree into 2. So all of the vertices that are in the untouched part of the tree still have the exact same subtree, nothing changed for them. And for many of these vertices along the boundary, what changes, for example, if there's this vertex, we're passing through it and then we will go into the right subtree, the left subtree still remained intact. So only the vertices that were actually visited during the split and modified are the ones that where something changed. And now, as we are returning from the recursive call, we can recompute the information for all of these vertices. This one is the last one where something changed, and everything beneath it, if there is still something, this is not a leaf, remain the same as before. So we just reuse the information from children to recompute the information in this one, and then we recompute all of the information there. So it doesn't change anything in terms of asymptotic time complexity. There is an extra constant amount of operation for each of the vertex. So when you are returning from the vertex, all the information below you in your children has already been corrected, and now you correct information that is stored inside your own node until you get to the very top, and you now have everything fixed. So you split the one tree into two, and in both the left one and in the right one, you have recomputed all of the values. So now at the top of the left one, you know the size of the left subtree, and the top of the right one, you know the size of the right subtree, and in each of them separately, you can now answer those queries. All right. So this is as far as I wanted to go about trees. We still have a few more minutes, so I will just talk about random stuff that comes to more my mind. And here is one question to, again, test your mathematical intuition a little bit. Balls into bins. So again, you can imagine it in the sailors and the cabins setting, but yeah, let's not disguise anymore that essentially what we are doing is some kind of hashing. So we have exactly n initially empty bins. We have a collection of n balls, and each ball will be taken and thrown randomly into one of the bins. So, like the ideal case there would be that each bin receives one ball. This is what happens on average. Like the expected number of balls that end up in a single bin is 1. This is the sailor's problem. But what happens to the maximum? So after you have distributed all of the balls, let's look at the bin that has received the most balls and write down this number. So for one particular experiment, you can get the value 3. Then you can be very, very lucky and get the exact smooth distribution and get 1. But then in the next attempt, you will get 4, then 2, then 3 again, then 5 maybe, and again 3, and so on. And this maximum is kind of interesting in the sense that what if you control the hash function? So for example, you can do something like universal hashing, where you don't actually hardwire one specific function into your program, but you use random choices to actually choose the hash function at runtime. So the person choosing and inserting the elements doesn't have cannot create one specific worst case for you, and you can guarantee that with high likelihood that values will be distributed as if randomly thrown into the array. So what if you control the hash function, you control the distribution of elements that are being inserted, but then an opponent controls the queries into the already constructed hash table. So in this case, the worst case that can happen will be that after the elements have already been inserted, the opponent will always be querying the specific element that fell into the most full bucket, and this will be at the end of the list for the bucket to cause you that each and every query into this hash table will have running time proportional to the size of the biggest bin. So in such a setting, it makes sense to ask the question, what is the expected size of the biggest bin? And now, here is where I again ask you to just test your mathematical intuition and try to guess what the answer will be. So in terms of the value n, what is the expected number of balls that will end up with the most full bin? Is this converging to some kind of a constant as n goes to infinity, or is this slowly growing as n grows? And if it is actually growing, what is the rough function? What do you think is happening there? Yeah, we are guessing.
I guess E.
Yes, so we got a guess of E and we got a guess of log n. Those are both very good guesses, simply because those types of things do happen, right? This is the most common thing. So if it is a constant, it's almost certainly E or something E related, because there will be some argument for that. You are summing up one over n or the n to the power of something, and it will always end up E. And if it is a function that grows, it should be something nice. It is not. Log n was closer, so the actual asymptotics of the size of the most full bin is that it is asymptotically, and almost exactly, in fact, the natural logarithm of n over the natural logarithm of the natural logarithm of n. So it doesn't go, yeah, it doesn't grow as quickly as log n, but only slightly slower than log n. And the math for this is not really pleasant, but it is on like understandable on college level. Again, I can link you a paper where this is done formally. So we know that this is how it behaves. So it isn't a constant. So in some specific cases of hashing, even if you had like a perfectly random distribution of your items into the hash table, it is not just the case that collisions will happen. It is the case that sometimes there will be, with high likelihood, a non-trivially full bucket of the hash function. And this is not a fault of your specific hash function, but this is a property of random distributions. Yes?
I want to complain that that's actually closer to E.
Okay. I think you may have a point as long as we are looking at practically sized values of n. Yeah. In terms of collisions happening, this is something that is, again, useful to know also for programming competitions. And this may be something I will finish my today's talk with. So, the very basic example of having collisions is the so-called birthday paradox. So let's talk about this for a little while, and then we will see some application of this also for the area of programming contests. So what is this? So suppose we have a classroom like this one, and there are two possible scenarios. One of them is that if we compare our birthdays, they will all be different. So each of us is celebrating birthday of on a different day of the year. And the other possible scenario is that two of us will share the same birthday. And of course, there are some specific settings, like where there are twins attending, where it is obviously one of those cases. But even if we assume that the people in the room were somehow randomly chosen and their birthdays are mutually independently random, then we have an actual mathematical problem. And we can ask again the question, which of these two options you should bet on? So if it is a 50-50 bet with somebody else, you are saying that one of them is true, the other person is saying that the other option is true, and you are willing to bet some money on it. At what size of the classroom should you switch your bet? So obviously, like if there are like 3 people total, then it should be very unlikely that 2 of them share the same birthday. So you should bet on the option that everybody's birthday is distinct. If there is a classroom full of 1,000 people, it is mathematically certain by the pigeonhole principle that 2 of them will have the same birthday, so we should bet there. Where is the split? And the reason why this is called birthday paradox is because even for many mathematicians, the initial intuition is quite off. So those of you who haven't seen this problem before, shout guesses. Where is the split?
10.
10. No.
Square root.
Square root, yeah. Square root is actually a pretty good approximation. So we can actually do the math, and the math is reasonably easy. So what is the probability of this happening, that everybody in the room still has a different birthday? So in order to calculate this probability, imagine that we send everybody outside, and then we are letting the people in 1 person at a time. And again, for simplicity, let's ignore the possibility of leap years and being born on 29th of February. It will work out anyways, but it just introduces biases, and biases make the other outcome more likely. So let's just assume that there are 365 days in a year for simplicity. When the very first person enters the room, it is still 100% guaranteed that everybody in the room has distinct birthdays. We can write this down as the probability of 365 over 365. When the second person enters, and we want still the probability that everybody in the room has mutually distinct birthdays, for this particular person, we only have one restriction. They cannot be born on the same day as the first person. And this will happen with the probability 364 over 365. And now if we assume that so far both of the steps were successful, so we have two people with distinct birthdays already in the room, and the third person arrives, the probability that this particular person doesn't break it is 363 over 365. And we can continue on, and we can keep multiplying these fractions, and after each step we have the probability that if you already sent k people into the room, this is the probability that all k of them still have mutually distinct birthdays. The moment when you should switch your bet is the moment when this probability drops below 1/2, and this happens for, if I remember correctly, I may be one off but not more, this happens for 23 people, so already less than the length of one single month. If you have 23 people in the room, you should already be betting on two of them sharing the same birthday and not on the opposite result. Asymptotically, if you have a calendar with n days, then this k, the value where the probability switches from one side to the other, is approximately, if I remember it correctly, equal to the square root of 2 times n. So why does this matter? And why should we keep this in mind in programming competitions? So first of all, if you want to use hashing as a data structure, you will definitely need to deal with collisions. So even if you, so the hash table in this case is the calendar year. The days of the calendar year are the individual buckets of the hash table. And as you are adding people into the room, you are distributing the items into the hash table. Each person will fall into the bucket for their own birthday. And what we are saying is that if the size of your hash table is n, then already around square root of n inserted elements, it is more likely that there is at least one collision than there is no collision at all. So if you want to store 100,000 elements, and you don't want to deal with any collisions at all, you would need an array of size not 10 to the 6, not 10 to the 7, but for, like, if you are storing 10 to the 6 elements, you need an array that is bigger than 10 to the 12, roughly. So the square of the number of inserted elements is roughly where it becomes reasonably likely that there will be no collisions. And this is something that we cannot afford, because the whole point of using hash tables is that we want to store elements, roughly one per bucket, and we want to totally spend roughly the same amount of memory as we have to. So the amount of memory eaten by a hash table should be linear in the size of in the number of items we are storing in the hash table, and not quadratic. And so this is the general observation, and one very specific place where this tends to happen is when you are using string hashing. So hashing of strings is a very popular technique to solve many string-based problems. And this is the technique that was developed originally for the Rabin-Karp string matching algorithm. So if you have a string, you can view the string as a large number. So each of the characters of the string can be considered a digit, like the ASCII code of the character. You can choose a base for the number that is bigger than the range of the characters you are using. And then you can take the value of the entire string, of this entire big number, modulo a randomly chosen prime, and you will get a hash of the string. And there are all kinds of tricks you can do with these hashes. If you like pre-compute the prefix hashes, you can then use them in constant time to compute the hash of any segment of the string, and then you can do like probabilistic comparisons whether two strings are equal. Is just by comparing those hashes. And ideally, again, this is a situation where you don't want to deal with collisions. So you want to say that if the hashes are different, then yes, I know with 100% certainty that these strings do differ. If the hashes are the same, you can say that, yeah, with high probability they are the same string, but it is also possible that I got a false positive and that I have two different strings with the same hash. In some cases, if the collisions are very unlikely, you can add an extra step if the hashes match, then you actually brute force check those strings for similarity. But what you ideally want to do is you want to rely on your hashes directly, and you want to just submit the code that is saying if the hashes are different, the strings are different. If the hashes are the same, the strings are almost surely the same, and I will rely on not being unlucky. And this birthday paradox is exactly telling you what you should do in order to have a high probability of this actually working. So you submit it and you get accepted. So what this is telling you is the range of your hash function that you need to have. So if, for example, you are going to have 10 to the 6 different strings, and for each of them you will compute the hash value, and you will then compare those values amongst each other. And you really want to guarantee that different strings will not create a collision, and you will not get two different strings with the same hash. Then you need to make sure that your hash values, so your hash table, as if, is much, much bigger than what would be required by the birthday paradox. So if you are just using hashes modulo one single prime that is roughly 10 to the 9, this is much too small, and you will get false positives, you will get collisions, because you are taking 10 to the 6 elements and you are throwing them into a virtual table of size roughly 10 to the 9. So there will be some collisions by the birthday paradox math. But if you use not just one random prime, but you use two random primes, then suddenly you have 2 to the 18 different possible hashes. And if you are throwing 10 to the 6 balls into 10 to the 18 possible bins, then the likelihood of randomly getting a collision is suddenly much, much lower than 1/2 or 1/1,000,000 or something like that. So two random primes in these specific settings, each of them chosen somewhere around 10 to the 9, should be more than enough to make it so that the probability of getting a collision is very, very small and probably shouldn't happen in 100 random test cases. So this is why it is good to keep this type of mathematics in mind, that if you are throwing many balls into a random hash table and you don't want any collisions, you need to make sure that the table is much, much bigger than the square of the number of your balls, and then it will work out nicely in practice. All right, and one final word of advice is that for many years, again, it was very popular to do this type of hashing in a slightly different way. And instead of choosing a random prime and computing modulo the prime, people were lazy, and what they were doing, they were choosing a random prime as the base of your number, and then computing modulo 2 to the 32 or 2 to the 64 by simply taking the hash as a, let's say, unsigned 64-bit integer and doing all the arithmetics in it, so the modulo was happening automatically. But after some years, it turned out that a few people, again from this programming contest community, spent a bit of time thinking about it and came up with specific counterexamples of strings, like just strings of 0s and 1s, for example. One of one's string, if I remember correctly, is the through Morse word. This is some very simple recursively defined pattern. And they have the property that regardless of what base you choose, if you specifically do it modulo 2 to the 32 or 2 to the 64, there will always be many false collisions, very many false positives for the hashing. So this is a specific counterexample, and especially in contests that are being written by Russian problem setters, this still nowadays, maybe some Polish contests, it's still the case that this, like, incorrect hashing killer is always inserted as one of the test cases just to mess with people. So do the hashing properly. So the way the mathematical guarantees are done for the original Rabin-Karp hashing are exactly based on randomly choosing the prime as the modulus. So you are computing everything modulo a randomly chosen prime, and if you do this, then you get the nice mathematical guarantees. Okay, so that's the last bit of today's lecture. Thank you for your attention, and good luck with the contest in the afternoon.